Hello, my name is Alberto. I'm a postdoc at SIT and USI in Switzerland. And together with my former team at the University of Seville, I would like to present you our work on online testing of RESTful APIs, where we will discuss the promises of our research, but also the challenges ahead. Well, web APIs, they're pretty much everywhere today, right? So if you think about companies like Twitter, YouTube, Netflix, Spotify, they all use web APIs because they allow to integrate services together in a very easy and standard way. So it is pretty intuitive to think that given the pervasiveness of these systems, it is very important to test them thoroughly, right? Because a single bug in any of those APIs can have a huge impact in all the other services using it and also all the users using those APIs. So talking about testing, I want to make a difference here between offline testing and online testing, which is what this work is about. So when we say offline testing, we refer to testing on a development environment. And when we say online testing, we refer to testing on a production environment. So whenever we say online testing of web APIs, we refer to testing of web APIs that are already deployed in production. So the APIs that we are already using. This is the agenda that I will follow today. So I'm going to provide some more background on testing of RESTful APIs. I will delve into the empirical study that we performed. And, this paper is about promises and challenges. So I will discuss the promises and the challenges. Web APIs nowadays are usually RESTful web APIs, which is the de facto standard for web APIs. And they're usually described with the Open API specification format, which you see here. As you can see, this is a machine-readable definition of a web API to describe it in terms of like the inputs and outputs. So the operations that you can perform, the expected format, and so on. The thing is that given a format like this, we can actually automate a lot of things, including testing. So for example, imagine the YouTube API. You don't have the source code, but you have the API specification. So you can actually automate the generation of test cases, so HTTP requests, which would look something like this. And then you can obtain HTTP responses, and up to a certain point, you can actually automate the assertions that you can perform of them. So this is actually what the research nowadays has been focusing on in the domain of RESTful API testing. And you actually see an explosion in the number of tools and approaches that have been coming out. These are just some examples, and they have all been proposed in the last 5 years or so. And in terms of the empirical studies that have been performed in all this time, I want to detail a little bit some of their features. So in terms of the case studies that they use, we see that there's a lot of variety. These approaches have been tested on a lot of different case studies, but we haven't really seen them apply to commercial APIs used by millions of users worldwide, which is the case studies that I will present you later on. Now, the experiments performed with these tools are usually limited either in the amount of time that they are performed or in the number of test cases generated with these tools. So maybe for fast web services, they are just tested for a couple of hours, or only a few thousand test cases are generated. Some of these approaches are tested on a controlled environment, so to say. So maybe just with a few APIs or just with APIs developed by the same organization that developed the tool. And finally, there have been a lot of different techniques proposed over the last years, but we haven't really seen studies comparing different techniques or leveraging many different techniques to see how they complement each other. On the other hand, in practice, we see that industry is more focused on providing testing and monitoring as a services. So you see these companies, Datadog, Rapid API, and Sauce Labs, they all provide testing and monitoring capabilities as a service where you provide information about your API. You just configure a few things, and then these platforms are able to continuously and automatically test your APIs all the time for days, weeks, or months. The thing is that they do not provide automated test case generation. So as a result, you see that there's a gap here between research, which is mostly focused on automated test case generation, but some of the results have only been tested, so to say, in lab settings, and practice, where industry is focused on providing continuous online testing of APIs, but actually they do not automate the generation of test cases. So the main aim of this work is to evaluate the feasibility of automated test case generation methods at the scale in an industrial setting, which is continuous online testing of web APIs. Now, to carry out the empirical study, we decided to use RESTes, which is our testing framework for RESTful web APIs. Also because it provides many different testing techniques, and this was a requirement for our study. But we soon realized that the monolithic approach of the tool would make it very difficult to scale at this level for what we wanted to do. So we actually had to decouple the architecture, and we actually had to come up with a few more components of REST test. And this is actually how the REST test testing ecosystem was born. We also took inspiration from the web-enabled simulation platform from Meta, where they envisioned the need of bots for automating certain parts of the testing process. So bots are actually highly cohesive and autonomous programs that can do different things. So for example, we use test bots, which are actually the ones testing the APIs. They are heavily based on REST test, so they provide different testing techniques. We also have garbage collectors, which delete all the resources generated in the APIs by the test bots. And this is what we call input bots, because they generate inputs for the APIs. We also have output bots, because they analyze API outputs, so API responses. For example, we have test reporters, which generate graphical test reports, and test coverage computers, which compute the coverage achieved in the API. All these bots are controlled by a controller component which starts, stops, and monitors them, but bots can also interact with each other. So for instance, test bots can actually trigger the update of test reports. Now, the number of bots is not limited, so more could be proposed in the future, and that's actually one of the lines of research for the future that we're working on. Talking a little bit more about test bots, because these are the ones in charge of testing the APIs, we classify these along 3 dimensions: write safety, test data generation technique, and test case generation technique. So you can have bots that are either read-only or bots that are read-write, so they can either create and delete resources and so on. We also provide 5 different test data generation techniques and 3 different test case generation techniques. So you see that combining all these dimensions, you actually have up to 20 or 30 different bots. We put this into practice. So as I said before, we wanted to evaluate the feasibility of different automated test case generation at scale. And for the empirical study, we decided to use highly popular APIs, including commercial APIs like YouTube, Spotify, industrial size open source APIs like Language Tool, and even APIs from public institutions like the American government, like FDIC. So in total, we selected 13 APIs, and we deployed a total of 228 bots in a public server, continuously and automatically generating and executing test cases in all these APIs over the course of 15 days, non-stop. So all this time, generating and executing test cases. And now I would like to talk about the promises of this work. So summarizing the results, what we achieved is we generated over 1 million test cases, out of which 390,000 failed. Let me just say that many of these failures were due to disconformities with the API specification. And we conservatively narrowed all these failures down to 254 bugs. Now, out of all these bugs, 65 of them have been confirmed in all these APIs. And in particular, the API developers of REST countries, YouTube, and Amadeus actually acknowledged many of the bugs and thanked us for our bug reports, because they could actually introduce bug fixes and documentation updates. This is an overview of when bugs are detected. So as you can see, about 90% of the bugs were uncovered in just the first 3 days of testing. But you also see that there are some bugs that took more time to be discovered. So this motivates the need for continuous online testing of APIs. Besides, you can also discover, as we discovered, reliability problems like service outages. You can also discover service regressions. So this all motivates the need for continuous online testing. What I would like to do now is to detail some types of bugs that we were able to uncover. And these are bugs that go beyond simple API crashes or disconformities with the API specification, which are easier to find. So this is an example. We can find bugs where we see that the API contains invalid data. So in the Amadeus API, there's an operation to look for hotel offers. So we found a hotel offer that actually contained a phone number that doesn't even exist. So this phone number should clearly not be there. And this was automatically found by one of our bots. We can actually find also inconsistencies between the API and the documentation. So for instance, in the YouTube API, there's the max results parameter, which you must not use in conjunction with the ID parameter. So one of our bots generated a test case combining both parameters, and it obtained a successful response, which was not expected. So we notified this to the developers, and they introduced a bug fix, because actually these 2 parameters cannot be used together. We can also find unexpected client errors where we provide a valid input, but we obtain a client error in the response. So for instance, in the DHL API, if you look for offices in Kosovo with the KB country code, you actually get a 400 status code saying that this country is not known, but actually it is listed in the documentation. So this country should be supported. And you can also find security vulnerabilities, for instance, in the OMDB API. One of our bots generated a test case using this special character for the sQuery parameter, and it obtained a 500 status code showing the stack trace of the exception with all the libraries and all the versions of the server, which is something that you should never do. Now, I would like to talk a little bit about the challenges. We identified several, but I would like to highlight two in particular. And the first one is the need for automated fault identification. So how do we go from all these thousands of failures to a few bugs? So we proposed a semi-automated fault clustering approach to ease this task, but actually we envision the need for more sophisticated approaches using maybe machine learning and clustering algorithms or approaches related to delta debugging. And the second most important challenge is the need for effective human interaction. So the thing is that bots work very well autonomously, but they could benefit greatly from some human interaction. For example, if we could confirm or discard faults that are reported as warnings, and then the bots could be retrained with this knowledge to be more useful in the future. This would be all from my side. Thank you very much for listening. And if you have any questions or comments, please do not hesitate to ask.